So using new software, realizing I get cut off at about 20 minutes. I probably only have 10 more minutes of video, so this is part two of the video. I'm just gonna kind of start over with this slide. All right, so where we left off, we were looking at carbon's atomic structure. All right, so on the far left, you can see that carbon has 6 protons in blue, and then our 6 neutrons in pink. All right, and then we see these variations or isotopes of carbon. All right, and so this means that carbon can offer different forms or isotopes, which are atoms of the same atomic number, but have variations in atomic mass, meaning that they can add on more neutrons. All right, and so starting from the left, we notice that we can see carbon on the periodic table. All right, this is its most common form, carbon-12, as it appears on the periodic table with 6 protons and 6 neutrons. All right, atomic mass of 12. All right, but in the middle, we now see that there are 7 neutrons, making it the atomic mass now carbon-13. All right, and again, in the last diagram, we see an atomic mass of carbon-14, all right, with 8 neutrons now in the nucleus. All right, so you can see on the table to the right here that adding neutrons to the carbon's nucleus makes it progressively less and less stable, all right, to the point of carbon-14 being considered radioactive. All right, so we actually use carbon-14. It's radioactive carbon-14, or it's also known as radiocarbon, for organic radiometric dating purposes. All right, so archaeologists use carbon-14, this isotope variation of carbon-14, to help date the ages of ancient organic remains, all right, such as fossils, bones, plant fibers, wooden tools, and weapons. All right, carbon-14 is unique and rare because it's created via these incoming cosmic rays, and I think a figure for you guys, yeah. So yeah, we have these incoming cosmic rays that we discussed previously, trying to get through the magnetosphere. Well, these rays from the sun, once again, are trying to penetrate through and bombard our upper atmosphere. All right. Once they do, they collide with nitrogen in the atmosphere to help form carbon-14. All right, because nitrogen, if you look on the periodic table, has a mass number of 14. So it collides with our cosmic rays. The carbon in the cosmic rays collide with nitrogen-14, making carbon-14. All right. So starting to kind of come together now. All right. And so now this newly formed carbon-14 combines with oxygen to make carbon dioxide, CO2. All right. So through the process of photosynthesis, carbon gets now cycled through all these organic things. All right. Us, plants, animals, everything. All right. And so just like iron, as we spoke about our basalt, iron-rich rocks, locking in paleomagnetic data, all right, this carbon-14 that we ingest, all right, can lock in how long ago it took for carbon to radiometrically decay, right, back to nitrogen. All right, so we can see this, all right, and so it's really useful because we can track this process and assign an approximate date to remains up to about 50,000 years ago. All right, that's kind of the threshold. Is up to about 50,000 years back, we can approximately date how old something was. So that's why when you go to the museum and you see the age of some sort of artifact. All right, that's how we got that age. All right, it was with carbon or radiocarbon 14 dating. All right, I also will post a worksheet that I think you guys will find useful on atomic structures. All right, I have a list of elements for you guys to kind of list out, being able to use the periodic table and being able to fill out the chart. All right, I've already posted it to Moodle, so you guys can look at that. Email me if you have any questions or just want me to double check it. All right, so this is how I'm going to end chapter 12, ending it at isotopes, and we will pick up with the rest of it. Talking about compounds and molecules, and move that to Unit 5, okay? And then as for Chapter 13 on this exam, we lost so much time last week that I also decided to filter out some of 13 and most of the material and just have you guys focus on just fusion versus fission, all right? That was kind of the bulk of it for us. Let me go back here. And just like Chapter 12, if we didn't cover it in class, it's not going to be on the test. We're going to move it to Unit 5, okay? So let's move on to fusion versus fission. All right, the last little bit of our chapter unit. All right, so let's imagine we have these little tiny charged particles zooming at the speed of light, all right, out of the sun's corona, right? Corona is Spanish for crown, the sun's crown, all right, and trying to now penetrate. They're leaving the sun and trying to penetrate Earth's atmosphere. Well, what do I mean by charged particles? All right, well, we have these fundamental building blocks of particles called photons, all right, photons, which are elementary particles that help make up the electromagnetic spectrum, all right, EMRs. We've already discussed this, I think, back in Unit 3. All right, so remember when I brought up the Planck era, going through the formation of the universe? Well, Planck, he was a scientist that helped discover quantum energy in the early 1900s. All right, and this quantum theory forever changed how we see matter on both the subatomic level as well as on an atomic level. All right, well, Planck, he got together with Einstein, all right, and together they developed this, what they call the Planck-Einstein relation, all right, where photon energy was directly proportional or correlated to the frequency at which this energy, this photon energy, is being transmitted and emitted, right? So this helped us further understand the relationship that we see between photons and how atoms emit light, all right, and these electromotive forces and radiation. All right, so in terms of light, all right, and I think this is chapter 11 in your book. We kind of breezed over it because we've already sprinkled it in Unit 3. But this is important. In terms of light, these particles bounce around, all right, and I'll just even kind of do this for you guys. They're bouncing around, all right, and collide and ultimately excite the atom, which then will cause these surrounding electrons, all right, let's pretend this is a little electron, all right, to spontaneously jump, and you can see in the figure, jumping to higher energy levels in the orbiting cloud, all right, and so this electron's now it's in its excited state at a higher energy level, and then it will fall back down to its original resting ground state. And so this excitement, this kind of going up and down, produces these tiny particles of light, all right, these light photons, which then get emitted. All right, and so this is how when we see this, photons are released to emit what we now can observe as the natural phenomenon as light. Let there be light, all right? So these little energized photon particles tie in with this concept of spectroscopy, all right? And so this is where, and I'll move on to the slide, where different atoms can emit different photons of light, all right, based on their electromagnetic spectrum. All right, so in your applied reading chapter, I kind of incorporated some stuff because this is interesting. They discuss something called the HR diagram of stars, which is a classification scheme to categorize different trillions of stars that we have in the universe, right? We have trillions, right? And based on their color, temperature, luminosity, size, mass, and overall evolutionary life stage. All right, so taking a look, I have two HR diagrams. They're both pretty similar, but I'll point out the differences. All right, you can see at the bottom of the x-axis, we're showing a decreasing surface temperature from left to right, and then from on the y-axis, up and down, we see luminosity increasing from going to the top. Our luminosity or brightness of the star is increasing. All right, and so we also see in the middle of the diagram, we have something referred to as the S-curve. You can really see it in the right diagram a lot better, where we have these what we call main sequence stars. It's the main sequence line, or the S-curve, or stars that fall on the S-curve are kind of in the prime of their life cycle. All right, they're still undergoing hydrogen to helium fusion if they're on the main sequence line. All right, so they're still undergoing nuclear fusion, and we discussed the process on Wednesday. All right, and another thing to point out, and this right diagram is pretty useful in showing this, that just because a star is bright does not necessarily mean that it's hot, right? So you can see our brighter stars, guys, yes, they are hotter in terms of our bright blue stars, right? But you can also have dim hot stars and bright cold stars, okay? So our sun is during its life cycle right now, it's currently classified as a yellow dwarf, all right? And in terms of it being an average size and mass, all right, you can see where it plots on the left diagram here. All right, it's not big at all. And it's actually relatively dimmer and colder relative to other stars. So it's not a big ball of fire after all. The sun will also start to go out over time, but as for now, it's still considered in the prime of its life, fusing hydrogen to helium, undergoing nuclear fusion. All right, before it, and this shows the life cycle, before it blows, it starts to, before it blows up to become a red giant, or it's going to expand and become a red giant in about 6 billion years. And then it will finally explode into a planetary nebula and eventually collapse in on itself and subside to end its life as basically the stellar graveyard, which we refer to as these little white dwarfs. It will be the sun's basically tombstone. It'll become a white dwarf, all right, by the end of its lifespan in about 10 billion years. All right, I think this is the last slide. All right, so to end our unit, let's just discuss some of the differences between fusion and fission. We discussed how nuclear fusion occurs when you fuse lighter nuclei to combine into heavier nuclei, right? And fission is the opposite. Remember, I said they were cousins to each other, right? They kind of function in the opposite manner, all right? Where you split heavier nuclei into lighter nuclei. So nuclear fusion takes place at extremely high temperatures. Remember, we're saying we need perhaps solar fusion. Our sun is at about 5,000 Kelvin. All right, we need these extremely hot temperatures where protons are so excited, and I'm going to try and do my little demonstration here. Let's see if it works. All right, protons are so excited. I lost my place. They're dancing around each other. All right, so let's just pretend the green side. All right. I have my protons, they're dancing around each other, and the temperature is getting hotter and hotter. So what happens when things get hot? They get more excited, right? And we have trillions of protons doing this in the sun, okay? Simultaneously, constantly, continuously, over and over again, all right? And so the protons are dancing around each other that they eventually start colliding and bouncing off, and yeah, they're doing this at first, but over time, they can't avoid their collisions anymore, that they eventually get stuck together, all right? They get smashed together, and now they're stuck, all right? And to offset this process, the mass of the protons is converted into energy. And so that's what the water is supposed to represent. It didn't really do that. Let's try it again. I usually soak these in water, and it works, all right? But yeah, so the mass of the protons, they smash together, and we see what's dripping out, leaking. I'm trying to do leaking energy, all right? And so, and during this proton dance, they've already leaked their energy. It's happening, every second we're leaking energy as these protons are smashing together, all right? And during this proton dance, we see the generation of neutrons take place, okay? So I'll hold these guys here. These are my 2 green protons, all right? And as they're stuck together, we now have I'll use orange, a neutrino, all right, emitted, and a positron emitted. Okay, so now I have these 2 products that were emitted out when these 2 protons smashed together, my orange neutrino and my red positron. Okay, and so, and I'll set these down. So we still have this going on over here. And then now I got these 2 guys that were emitted from those green protons, all right? And now they combine. Remember we talked about, what do they combine to make? A neutron now, all right? So my red and orange positron neutrino combine to make, now I have, pretend this is 1 neutron for right now, all right? And so all the pairs of protons, and this is happening all over the sun, all right? So now let's pretend we got this going on. That neutron finds that one of the protons, okay? So we're good. We got a proton-neutron pair. Another, now, proton-neutron pair. And pretend that's, right? What do they combine now to make, all right? We got helium, okay? 2 protons and 2 neutrons. We have helium, okay? So during fusion, the sun, remember I tried to represent that with converting to energy, the water leaking out, that's energy. We lose as much as 4.3 billion kilograms of mass every single second that is leaking and converting into energy. All right? And because of Einstein, we now know that we can change mass into energy, all right? We're not creating or destroying it. We're just transitioning from mass and converting it into the form of energy. E equals mc squared, all right? So while this is good and all, the technology behind this mechanism, nuclear fusion, is still quite far away, all right? Trying to recreate it here on Earth, all right? As it is hard to manipulate and control extremely high temperatures and energy, excitement levels to help initiate this proton-proton collision, all right? We have particle colliders. We just can't quite jump up to those high temperatures just yet here on Earth and try to manipulate to have protons colliding with each other, all right? So hopefully in the near future, there will be some technological developments in successfully harnessing fusion power, as fusion power is thought to be considered a very efficient, clean, limitless, viable source of energy that doesn't release any emissions or radioactive waste. All right, so once we can successfully figure out how to build and operate a solid and effective fusion reactor, nuclear fusion will most likely dominate the energy sector here in the future, right? And society's going to be able to utilize this energy. It's going to pave the way for the future if we can get nuclear fusion to work here. If we can kind of recreate what's happening in the sun and bring it down here on Earth, man, we're going to be good, all right, for the future. In terms of climate, in terms of providing needs to society in an efficient, cheap manner, right? It's going to be the future if it ever works, hopefully. And hopefully it's as good as they say. But lastly, nuclear fission, on the other hand, is when a larger atom splits into lighter nuclei, so the opposite process, as you can see here in this diagram. Nuclear power plants currently use fusion nuclear reactors to generate electricity, so that's what we have going on right now. It is much easier to control and operate the fission process, as it only requires little energy, less temperature, to split an atom into two. All right, it's harder to fuse light into heavier elements than it is to take apart a heavier element and split it into two. So this also means that the product energy is also small. All right, small input, we get a small output. All right, relative to the energy that we would theoretically be producing in fusion. Bigger input, bigger output during fusion. We don't get that with fission. All right, so there's also a lot of byproduct radioactive waste, all right, during nuclear fission, all right? So that's when they're talking about, oh, nuclear radioactive waste, how do we dispose of it, all right? So this can be a cause for health and natural hazard concerns, all right? We've heard about different nuclear power plants, Fukushima, Chernobyl, all right? There's already been different events that have happened in the past, and hopefully, we can work away from that, but, it's still a cause for concern, all right? And fission is also a very expensive source of energy, all right? And the benefits right now, all right? Otherwise, more countries would be implementing it. Either way, we're still a long way away from having alternative sources of energy as being our dominant source of energy to help generate electricity. All right, we're still in the beginning stages, running simulations, developing prototypes, but it still takes time before we can confidently say that the world's population will be able to run on smart, practical, affordable, clean energy. We're not quite there yet. We're ambitious, all right? People are starting to come up with ideas and methods, but we're not there yet. Right now, we're still using our conventional methods, and we probably will for the next few decades. I hope you got something out of this video. Good luck studying, and I will see you guys Monday. All right.